Good afternoon, students. Today we will discuss the forced vibration. Unit 3. The forced vibration. In this figure, we can see that a system is using. In this system, we are using a spring and a damper. Therefore, it is combined system of spring and damper. If we add any external applied force F0 sin omega t, then the system will convert Kx. Spring force is omega t minus phi. It is lagging the F0 by phi angle. So at F0 it is lagging my phi angle. Kx is phi angle less than omega t, and c omega x is damping force, which is 90 degree forward to spring force. The spring force is Kx, 90 forward of it is c omega x, that is damping force, and inertia force is 90 forward to damping force. Therefore it is mx omega square is inertia force, and it is, or in the other word, it is 180 from this x, and x is this, or equivalent diagram of this can be redrawn like shown in B. This Kx is in this direction, mx omega square is in opposite direction. So merging these two, we will get Kx minus mx omega square, and c omega is damping force. At y-axis it is 90 degree angle, F0 is our external applied force, and phi is the difference between these two forces. The equivalent force polygon is shown in diagram B. Now we will apply Pythagoras in this triangle, and these are the main salient points of this vector diagram. The displacement lacks the impressed force by an angle phi, omega t minus phi. Since x was omega t minus phi, the displacement is lagging phi angle from displacement vector, and spring force is always opposite in the direction to the displacement. In spring force is minus k, therefore it is again opposite to the displacement vector. The damping force lags the displacement by 90 degrees. Since velocity leads the displacement by 90 degrees, it follows that damping force is always opposite in the direction of the velocity, and inertia force is in the phase with displacement. The direction of x and direction of mx double dot mx omega square will be same. So now we are applying Pythagoras in this triangle, which will give us f square is equals to kx minus mx omega square whole square plus c omega x square. We will take common x, we will take x as a common factor. So the x amplitude will be equals to f0 divided by under root of k minus m omega square whole to the whole square plus c omega square. Now we are dividing k and denominator and denominator. So f0 by k, and in this k by k, omega m omega square by k, c omega by k. This k by k, f0 by k is known as static deflection with 0 degree, 0 frequency, and it is denoted by xst. K by k becomes 1, m omega square by dividing this k by m. This k by m becomes natural frequency omega n, this omega by omega n ka square. Similarly, this factor will become 2 zeta omega by omega n. We will divide this by cc and multiply this by cc. We will divide with m and will multiply it by m, and this will become 2 zeta omega by omega n as in unit 2. So the amplitude of this particular will be as shown in slide. X is equals to xt divided by this whole factor. And from this triangle we can also find out this tangent phi. Therefore phi is c omega x divided by k x minus mx omega. The x's cancel out each other, and therefore phi is equals to tangent inverse 2 zeta omega by omega n divided by 1 minus omega by omega n ka square. And this will this figure, and therefore particular part of this solution will be equals to x static sine omega t minus phi divided by this factor. So the complete solution xc plus xp is equals to x is equals to a2 e to the power minus zeta omega n t sine of 1 minus zeta square omega n t plus phi 2. This is exponentially decaying part, and this part is sine x statical sine omega t minus phi divided by this factor. This is complete solution for excitation by f0 sine omega t, forced vibration. And this is the diagram. Complementary part, it is in long exponentially decaying e to the power minus zeta omega n t, and particular part there is a sinusoidal wave. Tangent part is vanishes or stops as the time passes, but this steady state part is constant. So the combined or complete solution can be represented as shown in figure C. It is by superimposing these two, steady state and transient part. Transient part will stop after some time, but the steady state part is continued constant part. Now there is some various conditions of this force polygon diagram. First, when there is very low frequency, omega is very low than the net omega n, phase angle is 0, means phi is 0. If this phi reduces to 0, this comes down, and then this c omega x will becomes less, and this part will be ultimately becomes to 0. Therefore this f0 is impressed force will be balanced by this spring force, since this c omega x becomes almost 0. Therefore the impressed force balances the spring force at very low frequency. And second case, when omega is equals to omega n and phi angle becomes 90, then this condition is known as resonance condition. When omega is equals to omega n, and when omega is equals to omega n, a resonance will occur, and this 90 degree, then this f0 will be balanced by c omega x, and mx omega square will balance by spring force. Therefore the impressed force will be balanced by c omega x, impressed force balanced by damping force. Also the spring force and the inertia force are equal and in opposite at resonance. Third case, when omega system frequency is very high than the natural frequency, then the phi is more than 90, then the phi becomes more than 90, the f0 will be almost equals to, or f0 will be balanced by this inertia force. At very high frequency the phase angle is almost 180 degree, and this damping force will becomes almost 0. The impressed force balances the inertia force. These are three conditions of this force polygon diagram. And magnification factor. This x by x static is known as magnification factor. As shown in this above equation, x was xxt divided by this whole factor. Therefore, magnification factor is x by xxt. How much amplitude is magnified? X is pulse. How much magnified? At resonance, when omega equals to omega n, this factor becomes 0. Then the x by xt will be equals to 1 upon 2 zeta. Now we can also now we are discussing this magnification factor, this curve between omega by omega n and x by xt. Magnification factor on y axis and omega by omega n on x axis. It is like this. At 1, when omega by omega is equals to omega n, that is at resonance condition, and when x is equals to xxt, the magnification factor is 1, then this it is shown on this point 1. So we will start at 0 frequency. The 0 frequency means at this point 0. Magnification factor is 1. This x by xt is 1, independent of damping, that is x by xt, which itself is definition of 0 frequency deflection. The x will be equals to xt. At very high frequency, when magnification tends to 0, at very high frequency, when omega by n is very high, 3, 4, 5, then this x by xt becomes 0. It is tending towards 0, and or the amplitude of vibration becomes very small. There will be no amplitude of vibration. X becomes 0. At third condition, when omega is equals to omega n, this point omega is equals to omega n, 1 point, the amplitude of vibration becomes excessive. Amplitude becomes x becomes infinite almost, and a small damping decreases with increase in damping. As we can see, at high it is 0. For 0 damping at resonance, the amplitude is infinite theoretically. At 0 damping, this zeta value of zeta is 0. The 0 damping resonance and the amplitude. For 0 damping at resonance, the amplitude is infinite. The x is infinite. And one conclusion from this graph is showing in this slide is, it is seen from these curves that the response of a particular system at any particular frequency is lower for higher value of damping. As we are increasing the value of damping, zeta जैसे जैसे बढ़ा रहे हैं 0, 0.05, 0.5, 0.01, ये the amplitude x by xt is decreasing, कम हो रही है इसकी वैल्यू, damping कम होती जा रही है. At any particular frequency, lowering the higher value of damping. In other words, the curve for higher value of damping lies below those of the lower value of damping. As we are increasing the damping, it is coming down. The amplitude is becoming low. X by xt की वैल्यू कम हो रही है जैसे जैसे damping बढ़ा रहे हैं. This is about this curve, magnification ratio and frequency ratio. Now second curve is showing about the phase angles. This curve is showing the graph between phase angle. Phase angle is varying from phi, is varying from 0 to 180. Phase angle is varying from 0 to 180. At 90 degree, it is 90 degree. At 90 degree, omega is equals to omega n, and it is the condition of resonance, as we have already discussed about it. It is 90 degree at resonance and is independent of damping. Over a small frequency range containing the resonance point, the variation of phase angle is more abrupt for the lower value of damping than in higher values. Now this one important factor here is this line, dotted line of zeta 0.707. Above this there is amplitude peaks. As we can see, this is amplitude peak, this is amplitude peak, and others are amplitude peak. And below this 0.07 there is not amplitude peaks, and the amplitude is decreasing, magnification factor is decreasing, it is less than 1. As we are increasing the zeta, जैसे जैसे zeta की वैल्यू बढ़ा रहे हैं, मैग्निफिकेशन फैक्टर कम हो रहा है, मैग्निफिकेशन कम हो रहा है, एम्पलीट्यूड कम होता जा रहा है. So if we are, it should be carefully seen that the maximum amplitude occurs not at the resonant frequency. Maximum, it is not at resonance frequency at 1, it is not at the peak. So for maximum amplitude occurs, we are differentiating maximum amplitude magnification factor with omega by omega n, and this value comes at 0, and at omega by omega n will be, omega p by omega n will be equals to 1 minus 2 zeta square ka under the root. So that particular zeta, this will give us zeta value of 0.707. At below this 707 there will not be any peak, and above this 707 there will be peaks of amplitude. Now we have understand the force vibration. Thank you very much.